going? Okay, so remember that in all of these cases, like every other reaction, you're going to be consuming reactants, right? And one of the things you got to remember about these is, did you guys catch on where we talked about the pre-reduction, pre-oxidation? So if you want to measure one species of something, you have to get it all oxidized to one state, don't you? Much like we did in the iron lab. Remember how we did that? We oxidized all the iron. And then it was all in that same form, so it all made the same product, right? Okay. So yeah, that's just the table. It sums up everything there. These are permanganate titrations. Remember, the permanganate needs to be recalibrated constantly, okay? So you need to recalibrate it pretty much before any major experiment, all right? It's not a primary standard. So, okay, let's look at the oxidation with Ce4+. So the Ce4+, this binds the anions right here. Variation of the Ce4+ to Ce3+, so, putting on that electron. Formal potential is indicative of these interactions. So right here's the formal potentials when you put this in each of these, okay? Okay. So Ce4+ is yellow, Ce3+ is colorless, but the color change is not distinct. What not distinct means that the human eye can't detect when this color change happens with any sort of regularity or accuracy, okay? So you'll see a change, but you might be way past your equilibrium point by the time you realize it's the equivalence point, excuse me, equilibrium, jeez, just keep doing that. Equivalence point by the time you notice it, okay? Or you may think it changed because you're looking so hard at it. They're just not distinct enough for you to tell, okay? Think of it as the difference in color isn't great enough for you to be able to tell. That's probably the best way to do it. Like the other ones were much more distinct colors that humans are much better at seeing. We have a yellow sun, right? So that kind of gets filtered out of our eyes, right? Yeah, yellows are pretty hard for people to differentiate. But like pink was clear, now it's pink. That one's easier, right?
So are some of these actually based on just human eye? We see the color change?
That's what you typically use indicators for, yeah. But you can also use this with a spectrometer to measure the color change. This is not a distinct color change that it doesn't happen. Remember that what you're looking for is a delta of change, okay? If the delta of color change of that frequency shift is not large enough per milliliter added, then it's not going to be very good to use as an indicator or something, right? This would be less than the human eye could even possibly do. You could probably find a visible light spectrometer that could do it. Maybe. I wouldn't bother though. Like there are so many more better choices. Just not necessary. So ferroin and other phenolphthalein redox indicators are well suited to titrations with Ce4+. We already have much better indicators that we can use and couple it with the Ce4+, okay? Which is why I would never bother using the Ce4+ color change to try to do any of this. Ce4+ can be used in place of potassium permanganate in most procedures. Why is this important? Well, Ce4+ is a much more stable agent. It's not going to oxidize everything around it all the time, and you have nothing left by the time you want your experiment done. It won't do other reactions if you have other stuff in there. So for example, potassium permanganate man, it'll oxidize everything. It'll oxidize a double bond if that happens to be around into two carboxylic acids, right? It oxidizes everything all the time, and it gets consumed because of that, right? Whereas this is not quite as strong. It's nowhere near as strong as an oxidizing agent, okay? All right, so this is orange dichromate ion. This is a powerful oxidant that is reduced to chromic acid in acidic solutions, which is what we see right here. That's the potential of that. So dichromate is a less powerful oxidizing agent than potassium permanganate or Ce4+ in acidic solutions. In basic solutions, the dichromate is converted into a yellow chromate ion. This oxidation power is nil, doesn't have any oxidation power. Notice the E0 value of this. 0.12, right? Obviously, that's not doing a lot of oxidation, right? It's not a powerful oxidizing agent. It is, yes. It has basically no potential. You'd have to, well, okay, so remember that, so as an oxidizing agent, you want this reaction to go this way, right? To take away electrons from the other thing. And so this is the potential, the draw for that to happen, okay? This is essentially the power that moves from this side to this side, right? Does that make sense? So this tells you how strong of an oxidizing agent this is. This, in fact, is not even an oxidizing agent. This is an extremely mild reducing agent, because it would go the other way. It would actually provide electrons preferentially. So if you had a 0 here, it will oxidize things that were negatives. But things that were positives or zeros, it won't oxidize. And remember, 0 is H+ taking on electron. So that's not, I mean, that is not typically what we would think of as a great oxidizing agent, right? That's like the cutoff what we think of things that are metals that are incredibly, hold on to electrons incredibly weakly, right? Is using acid H+. So you can use a 0 as a H+ as an oxidizing agent though, right? Like it does work with certain metals. You have to get things like iron though, right? And tin. There are so many metals that don't oxidize, and of course, if you're not oxidizing metals, then you aren't oxidizing any non-metals either. So, yeah. So again, it's relative, right? Everything in voltages, everything having to do with these potentials is always relative, okay? Because the 0 point is a very specific reaction. It's not a, in fact, that's why this is that's why typically these would be called like a degree, which they don't call them here, but it's funny that this is a relative scale. Did you guys know that we don't actually know where the 0 potential energy actually is? Like we set a value for 0 potential energy, but nobody's ever been able to experimentally confirm that value in any way whatsoever. It's hypothetical projection from what we know, but in fact it very likely is not true. Like more recent experiments having to do with quarks and quantum show that there's probably a whole level of energy below that that we just haven't been able to play with. Yeah, so it's kind of an interesting thing. But anyways, this neatly sidesteps all that because we know our 0 point, right? It's H+. Okay, notice, by the way, that the reason we're talking about this dichromate is the potassium dichromate is actually a primary standard. This is extremely stable. You can keep it on shelves. It won't gain a lot of water over time as long as you store it properly. It That's just a great primary standard, okay? And so you can use this to standardize other solutions if you need. Or you can just directly use it if you can. Remember, it has to be acidic conditions, and then it's an okay, kind of weakish oxidizing agent, okay? 1.36 is, moderate. Stronger than most metals, but not all metals. So, solutions are stable and cheap. We used to make huge batches of this when I went through this as an undergraduate. Though an interesting side note is chromic acid actually will convert over time, and you'll start getting algae blooms growing in your damn solutions. Because chromium 3+ is actually a nutrient. So we'd come back after vacations, and sometimes our bottles would have these huge algae blooms in the middle, these white ones. Yeah. Really kind of a pain in the ass. Anyways, so indicators such as diphenylamide, sulfonic acid, or diphenylbenzidine sulfonic acid are used to find dichromate endpoints. This would be your indicators that you typically use with it. Reactions can also be monitored, of course, with electrodes. Though remember that then you have to deal with the lag and response, right? So it typically, if you don't know where your endpoint should be approximately, those are going to take much longer to titrate typically, okay? The visual indicators are usually much faster. So typically what people do is they'd use a visual indicator, do one titration, and then they would use a electrode to do the actual work. So then they would know about where it ends, right?
So it'd be like, find out like the range and then use the electrode.
Yeah. And that way you can, put it in until the bottom of the range, and then put drop, wait for it to go, put a drop, wait for it to go. Yeah. Keep in mind though, all of these you can always do the grand plots to get where the endpoints are, to get where the equivalence points are, if you use electrodes. So
in the lab that we're doing right now, when we add the O and something, I forget the name of it, it turned red. Would that happen if it wasn't, if we didn't add enough, if we didn't get it away from acid, most we didn't get it up to like a 3.5 pH, or would it still happen?
Yes, it would mostly happen.
So another way of doing it in a way would also be to add that first and then adding the drops.
It would happen. Like that wouldn't tell you the 3.5 pH. Yeah, unfortunately, no. Though, yeah, any visual indicator you would try to use in that would cause you problems. Yeah. It's not that responsive. And there is some variance, and that's actually one of the reasons that you want to get them all around the same pH. That way there's not enough variance for it to affect your beer slot. Like, you also would have a problem if you were just doing that they are going to be different colors, because each of your standards will have different concentrations. So like, if you tried to match colors, you'd actually screw everything up, right? Okay. Yeah, but yes, it does change colors a little bit because the iron. Anyways, notice, by the way, you typically use the calomel electrode. This is not a 0, so you always have to subtract that amount off, right? Which is what last chapter was talking about, in case you're ever confused about that, which happens. I'll be honest, I was confused about that when I first got it. It took me like a study session before I realized, oh shit. It just means subtract off that. The tables can be confusing. All right. This is not as strong of an oxidant as the potassium permanganate or the Ce4+. Both are stronger. In fact, this is sort of I'm giving you a line of strength here, right? We have potassium permanganate at the extremely powerful oxidizing agents. CE4 plus is the, you know, a little bit above moderate. And then this one is sort of our weaker one, okay? And that's not necessarily a bad thing. It's just what you can use it for, right? If you put in an oxidizing agent with something's a more powerful oxidizing agent, then it's no longer an oxidizing agent, is it? It's a reducing agent. Okay. Does that make sense to everybody? So this is used for determination of iron 2 plus here. This right here, by the way, is the indicators if you're curious. So right here is actually the reaction that causes this indication here. So these are the diphenylamine sulfonic acids. See the sulfonic acids, the amines. And this is actually the reaction right here that causes that indication. So it's in reduced form is colorless. When you oxidize it, it goes to violet. Notice violet, blues, and reds typically are the best indicators because they're what your eye looks for in danger, right? When you see any of those colors, you go either food or poison. One of the two. Okay? So when a reducing analyte is titrated with iodine to give I2, the method is called iodometry. I know. The naming, huh? Don't you love it? Everything's metry. So in iodometry, an oxidizing analyte is going to be added to excess I2 to produce the iodine, which is then titrated with standard thiosulfate solution. The molecular solubility of iodine in water is enhanced by completion with iodide. This is completion with iodide right here, by the way. If you try to dissolve I2 crystals in water, it will essentially not dissolve at all. Did you guys ever use any iodine solutions? In general chemistry, you should have used an iodine solution for a rate of reaction lab? No? Okay. Okay, anyways. So this iodine is sublimated and you get it as iodine crystals. And then you can get like Ki for the I minus, the iodide. If you only mix the iodine in with water, you essentially get almost none of it dissolved. It's more soluble in alcohol, but that's beside the point. You have to complete it right here. You have to complex it with the I minus. It forms I3 minus, which is then soluble in water. Keep in mind I2 is neutral, right? And so it's a nonpolar. This, on the other hand, would have a charge, right? So the water can surround it in its normal complex structure. Notice this is not actually that soluble, which is a common problem people do. They try to make iodine solutions that are too high concentration. Interesting note, 2% iodine is, above 2% iodine is actually a controlled substance. Apparently it can be used to make meth. Just funny, because you could just take 1% and boil it off, right? And that's not a controlled substance. I don't know what the hell the government was thinking. But anyways. So when you use iodine, one of the most common ways to use iodine is with starch. So starch is a great indicator for iodine because it's cheap, easy, works well, just a great indicator. In iodometry, titration with I3 plus, or 3 minus, excuse me, wow, I don't know why I'm going with that charge. Starch is going to be added at the beginning of the titration. The first drop of excess I3 after the equivalence point will cause the solution to turn a dark blue color, okay? Keep in mind that this dark blue color will be very clear and see-through at the beginning because it will be low concentration, right? It's one of the most common things I see students when they first do this have troubles with is they think it should be dark as in you can't see through it versus dark as in it's like royal blue versus sky blue, right? Does that make sense? Okay. Like it'll still be not darkening the light that goes through it. Does that make sense? It's just a color. All right, so iodometry, again, titration of I3-. Notice the difference here. IOD-I, iodo. I know, it's hard to hear, okay? So notice the difference. The one with the I is titration with I3-. The one with the O is titration of I3-. So you'll be putting a titrant in it, right? Okay. So starch should not be added until right before the equivalence point. Otherwise, you would bind all of your starch and you'd have difficulty to tell, right? It would slow down your titration because you'd have to remove the iodine from the starch all the time. Does that make sense? The starch iodine complexes are temperature dependent. And in fact, you can do some fun little demos with this if you want. If you take a starch iodine complex and you put it on a hot plate and heat it, you'll actually cause the color to change. So you can literally go from like hot to cold and the color will change. Okay? So cooling it in ice water is actually recommended for maximum sensitivity. And this is because, remember when it forms that complex, the starch chain has to wrap around it. Remember that from the beginning of the chapter? What happens when you heat a long chain like that? It starts flip-flopping and typically straightens out. Like DNA does that, starch does that, they all do that, okay? Which is also why starch solutions lose their viscosity when you heat them, because they are not tangled together as much, right? They straighten out. Okay, so preparation and standardization of I3- solutions. The triiodide is prepared by dissolving solid I2 in excess Ki. By the way, this is actually one of the most important ones that I'll ever teach you. Iodide solutions are incredibly common to have to be made by just every chemist all over the damn place. Like if you go to grad school, you're going to be making these for labs, and if you go to businesses, iodine solutions are pretty common. I did not pay attention to this when I was in undergrad, and I had to figure this one out myself. So here's the one you want to pay attention to, okay? You ready for it? All right, so the sublimed I2 is going to be pure enough to be a primary standard, but it will evaporate if you leave the cap off. So it evaporates while it's being weighed. Slowly, but if you take your sweet time on this, you will have a noticeable difference, okay? So instead, what you want to do is approximate the amount is rapidly weighed, and then the solution of I3- would be standardized by a pure sample of your analyte or by sodium Na2S2O3. Okay? You can also do difference weighing. That's one of the ways I do this. That gives you a better approximation. If you need it more accurate, you would want to still do this standardization, okay? It gives you much, much better accuracy. Acidic solutions of I3- are unstable. So if you have it as acidic solution, it will not be stable. It will be unstable. The standard I3- can be prepared by the reverse dispropionation reaction. This is the reverse dispropionation reaction. So you have IO3-, you have iodide in solution, and then you have an acid. And this would give you the I3-, 3-, and H2O. That'd be it right there. Okay, here we have sodium thiosulfate. Sodium thiosulfate is going to be universal titrant for I3 minus. That's the one we were just talking about, by the way. The Anlitor sodium thiosulfate. So in neutral or acidic solutions, the I3 minus can oxidize thiosulfate to tetrathionate. So this right here is the reaction. See, they react a 1-to-2 ratio. And you would get tetrathionate. This is tetrathionate right here. Okay? So in a basic solution, I3 minus will disproportionate to I minus and HOI. This can oxidize S2O3 2 minus and SO4 2 minus. S2O3 minus being this right here, the thiosulfate that we were just talking about. So you can prepare stable solutions of the sodium thiocyanate, or oh, good God. I'm having one of those blooper reel times where I get the words from other classes coming out of my mouth. We were just talking about that damn solution. Sodium thiosulfate. So you can prepare a stable solution of sodium thiosulfate by dissolving the reagent in high-quality, freshly boiled water. Remember that when you can boil off the CO2 in water. That's what you're doing. So dissolved CO2 is going to make the solution acidic. Remember that would promote that disproportion of S2O3 minus. So remember if it's an acidic solution, you'll have H+, right? So it'll cause this reaction. By the way, notice it actually produces a solid. So at some points, you may actually be able to see this happen. So if you did not boil off the CO2 appropriately, or your solution was too acidic, you may actually see some solid. It's yellow, so it actually is reasonably visible, okay? Metal ions catalyze atmospheric oxidation of thiosulfate. So for example, copper in water is going to catalyze this reaction. Which is why we said high quality, freshly boiled water. So something that has had its ions removed to a high degree. So deionized water. The deionized water we work would not actually make a solution that would give you a perfect standard. You'd be much better off with like an 18 megohm water. Would give you a great solution. Do you guys know what 18 megohm water is? So the resistance of the water tells you how many metal ions is in it. The higher the resistance, the less metal ions are in it. Okay? And so it's extremely purified water. The units purified, though, are very expensive. And if you have to buy it by the bottle, it's actually very expensive as well. But if you work and research with people that have it already, they can make lots of it for the units and just give it to you every week. Okay? So make friends or have a big budget. One of the two. Okay. Analytical applications of iodine. Reducing agents can be titrated directly with standard I3 minus in the presence of starch. This is one of the most common uses for this. For example, iodometric determination of vitamin C is in your lab book actually, and it is a very common lab and a very common way to do the determination of vitamin C. So here's ascorbic acid, which is vitamin C. This is the reaction with the I3 minus. There you go. Have any questions? No? Okay. Okay, so oxidizing agents can be treated with excess I minus to produce I3 minus. The iodometric analysis is completed by titrating liberated I3- with standard thiosulfate. So this would be a form of back titration, right? Starch would then be added right before the endpoint. Remember, you don't want to, if you have lots of I3- in your solution already, you don't really want to add the starch yet, okay? You actually would, it's better if you can get closer to the endpoint first before you add the starch. Otherwise, it binds the iodine and makes it very difficult to do the titration, okay? All right, so these are some different titrations with that standard triiodide or iodometric titrations, if you want to use the wording for it. And there you go, the different notes. Notice it is an extremely common method. So, see this? All the other ones have like little tiny tables. Look at that. 2 full-page tables. Damn, right? Yeah. Iodometric titrations are very common because it's just a very, very useful titrant.